Okay, so let's continue in our discussion of equal time quantization. And I want to ask a question now. So the question I want to ask is, what generates time translations? So this should seem like a very sensible question to you. Um, You're used to Lie groups. The group of time translations is certainly a Lie group. So we can ask, what's the generator of that translation? So if we were to look at a little transformation, little time transformation, what is the Lie algebra element that generates that time translation? And I think you know what it is. The answer to that question is given by the Schrödinger equation. So the Schrödinger equation tells us that I h bar d by dt acting on psi is equal to the Hamiltonian times by psi. So if you ask what generates time translations, the answer is obviously the Hamiltonian. And that's what's coming from Schrödinger's equation. What is the solution to this equation? Well, psi at time t is equal to u of t times by psi at time naught. And u of t is equal to e to the minus I over h bar ht. Now, I'm sure that you've seen this in your first course on quantum mechanics. Let me just point out to you that maybe you can look at this with fresh eyes in the sense that u of t generates a time translation. So it's an element of the group. And how are we getting it? We're getting it as usual by exponentiating an element of the Lie algebra. So the Hamiltonian would live in the Lie algebra. It's associated with an infinitesimal time translation. It generates an infinitesimal time translation. And you exponentiate that to get u of t, the element of the group, which generates a finite time translation. Now, when you are solving the Schrödinger equation, the time-dependent Schrödinger equation, so let me just outline it in red. This is a first-order differential equation. So when you integrate it, there should be one arbitrary constant. And of course, that arbitrary constant is psi of naught. That is the initial condition. Good. And what we now have, so this is rather interesting, psi of naught lives in the slice at t is equal to naught, whereas psi of t lives in the slice at time t. So what the Hamiltonian does, let's draw it on our picture here, it takes us from one slice and moves it into another slice. So now the Hamiltonian allows us to produce the time evolution operator, and the time evolution operator will move us between different slices. So this different collection of Hilbert spaces that we have, one for each different slice, are related by time translations. Time translations are a unitary transformation. So what that means is all of these different Hilbert spaces are related by a unitary transformation, and that means that they are equivalent. Because of that, we can actually identify all of these different Hilbert spaces, one for each time slice, and be left with just a single Hilbert space. We can imagine dynamics happening inside that single Hilbert space. So as time evolves, well, we'll move from one slice to the next slice to the next slice. And now, because we've identified all of these Hilbert spaces, that time evolution becomes a motion inside this single Hilbert space. And now I hope that you can see that this is the picture that you're used to for quantization. So now let's just make a few comments, okay? So let's just say some comments. So if you look here, time has played a special role. So uh, let's say time played a special role. So let's see what role it played. So the first role it played is that we used it to foliate space-time. So all of these different leaves of our foliation, or all of these different time slices, these were constant time slices. So we have constant time slices. And we had a Hilbert space associated to each space, or a Fock space associated to each slice, or a phase space associated to each slice. But this is what we got when we foliated space-time. The next thing that time allowed us to do, we were able to calculate conjugate momenta. Okay, so let me just remind you. So that, for example, was this equation pi of t is equal to dl dx dot I of t. So this was an equation that held on a specific slice. So on each slice, we could define the conjugate variables, and time was playing a role when we did that. We took a derivative of the Lagrangian with respect to x dot. In the case of quantum field theory, we took a derivative of the Lagrangian density with respect to phi dot. So phi dot x dot, the time derivative of the coordinate or the field, that was playing a special role. And then finally, we were able to impose some quantization conditions. And the quantization conditions, so let's say quantization conditions, they were given as equal time commutators. So they're often called equal time commutation relations. They might be called equal time quantization conditions, anything like that. But the quantization that we used also depended on the fact that we were using time to foliate our space-time, and the quantization conditions, if we want to quantize the Hilbert space, well, the Hilbert space lives on a given slice, so whatever quantization condition that we have, that must also live on a specific slice. Now, it turns out that, okay, so we've used time, but time is not the only choice that you can make. So you might use some other coordinate in the theory. It may be, so we're going to soon use light cone time. So it'll actually be a linear combination of time and space. And we're going to let that play the role of time. So what do we mean by that? Well, we're going to use this to foliate our space-time. So now our slices are not going to be surfaces of equal time. They're going to be surfaces of equal light cone time. Then we're going to take a look at conjugate momenta. And we're going to define the conjugate momenta using light cone time in much the same way that we use time. And finally, we'll impose some quantization conditions on each of these equal light cone time slices. So we'll get a different quantization of the theory. Now, of course, any physical question that you ask, like, for example, a correlation function, an S matrix element, anything like that, you could do the calculation in equal time quantization, or you could do it in equal light cone time quantization. You'd get the same answer. So these are the same theories. We're just using a different method to quantize these theories, to quantize the theory, but they are the same theory. Once we've done light cone quantization, we'll then be able to move on to radial quantization, and that's the quantization that's really useful for conformal field theory.